All right, our first speaker is Scott Campbell from Michigan State University in the field of nuclear physics, and he is an SSGF fellow who is doing his practicum at Lawrence Livermore National Laboratory. So please welcome Scott, and you'll get indicators from our timekeeper on when to break for questions.
Awesome, thank you very much. All right, let me just make sure. Cool. Hello, everyone. It's very nice to be here. I've had a great time during my stint in this fantastic program, and it's really an honor to be here and discussing a relatively small part of the research that I've been a part of during my PhD program. And so I'll give a little bit of a caveat. So I'm more in the nuclear science, fundamental sciences side of things, which is perhaps a little bit different from a lot of the other talks that you'll probably be hearing this week. So I'll try and give you a little bit of an overview and an introduction to that at the beginning of my talk, before moving into a little bit of an overview of our experimental facilities and some of the incredible opportunities that we have over at the facility for our isotope beams at the Michigan State University campus. And then I'll go into one of the really nice science results that we were able to see in the last couple years. And so with that, let's get straight into it. I think it's really important, especially for us in this nuclear field, to really consider this question that I think often gets overlooked a lot. And that's, why does a nucleus exist in the first place? If we have this really naive intuition, we have a bunch of these positively charged protons packed super tightly together. From just a simple Coulomb repulsion, those should just instantly fly apart. But we know they obviously don't. And that reason is because of the nuclear strong force. And essentially, at these very short distances, it's able to overcome that Coulomb repulsion, and it is essentially converting some of that proton and neutron mass into this binding energy holding the nucleus together. And so a consequence of this is that once we weigh the nucleus, we actually see that it's always lighter than if we just considered the sum of the proton and neutron masses on their own. And that difference is what we call the binding energy, and that is particularly unique to each nucleus, and it kind of serves as this nice fingerprint telling us a lot about the interplay of nuclear forces, how that nucleus is prone to decay, and all of that can only be determined experimentally. And we rely on these precise mass measurements of these nuclei to determine that binding energy and, again, inform our understanding of nuclear forces and all of the underlying science that keeps these nuclei stable or unstable. And so if we kind of take a look at the status of nuclear mass measurements, this chart is perhaps not familiar to everyone. It is the chart of the nuclei where the y-axis here is giving you the different elements, and the x-axis is giving you different neutron numbers on that element. And so these black boxes that you kind of see in the center are all the stable isotopes. These are things that live for millions and millions of years, everything that we see on Earth. And as we kind of go to the sides are where we start entering this realm of rare isotopes, things that decay on relatively short time scales, down to milliseconds, nanoseconds, or even shorter in some cases. And so the general trend to note here is that as we are getting farther away from this valley of stability, we start getting lower and lower mass precision, up to the point where we have currently no mass measurements or, frankly, insufficient precision to tell us anything of importance for nuclear science. And those nuclei are particularly important for nuclear science because they are very challenging for our current theory models to understand and predict. But there's also this interesting emergence of exotic nuclear features, things like exotic shapes. Halo structures are one of those. And just to give you an idea of what a halo structure looks like, it's when we have one or more of the core nucleons extending very far from the rest of the nucleus. And in this particular case here, we have lithium-11, which is a 2-neutron halo, and it has a radius that is comparable to that of lead-208. So a small number of nucleons can have a much larger radius. And there is a particular interest in this isotope Aluminum-22, which is seated right at the proton drip line. And this nucleus was thought to exhibit a one-proton halo, where just one of those protons is extended further out. And this was of particular interest for a lot of science, understanding nuclear forces. And so that's something our research group was particularly interested in investigating. So before I can really get into the science, I think it's important to take a step back and look at how we're actually producing these rare isotopes to begin with. There's a lot of facilities around the world that are specialized in rare isotope production. The one that we have in the United States that is particularly good is called the Facility for Rare Isotope Beams. This is a US DOE lab that is a user facility, and its primary feature is this 400 kilowatt primary beam power, which is one of the highest intensity beams for rare isotope production in the world. And this starts with our superconducting linear accelerator, where we are accelerating our stable beam up to about 50% of the speed of light, where it ultimately hits a carbon target, producing a cocktail beam of these rare isotopes. We then want to separate those rare isotopes for just a single one that we want to measure or study, and that's done with this in-flight separator. And the big picture here is that all of this is done incredibly fast, and it provides us access to all different elements and all different isotopes, even those with incredibly short half-lives, all of which is incredibly important if we want to start reaching the limits of stability for these nuclei. And so where we're actually doing these nuclear mass measurements is at this low energy beam ion trap facility at FRIB, where we use penning trap mass spectrometry. And just to give you a little bit of an overview of what's going on here, we have this electrode structure, which we call a penning trap, and it is seated deep inside a very strong magnetic field, which is, in our case, a 9.4 Tesla superconducting solenoid magnet. This is our most accurate mass measurement technique to date. We really can get a complete idea of the nuclear mass with just about 100 ions observed, and we can access half-lives down to about 50 milliseconds. And with that in mind, we are able to achieve really high precisions, things down to parts per billion, and even in some cases, we've reached 1 part per 10 trillion mass precision. And these are completely sufficient to understand nuclear forces and all of the interesting nuclear science that are of critical interest for the field. And so just the basic idea of how we're actually performing this mass measurement is kind of coming down to this really simple relationship. In our strong magnetic field, if we have an ion, it will rotate at a characteristic cyclotron frequency, which is characteristic of its mass and its charge. And the penning trap itself is just providing an electric field to confine that ion in 3 dimensions so that we can study it for extended periods of time. And if we look at the actual picture of what the ion's doing in the penning trap, it's a little bit complicated, and it's a little bit beyond the scope of this talk, but I think it's just interesting to get a kind of an idea of what is going on inside this detector. And so if our mass measurement really comes down to these cyclotron frequency measurements, how are we actually doing that? One of the ways is with this so-called PICR technique. This stands for phase imaging ion cyclotron resonance. The details, again, are perhaps not so important, but I think it's really interesting to see the simple mechanism wherein we're doing these measurements. And so inside our penning trap over here, we have our ions rotating in a circle. And if we measure the position of those ions at 2 different times, t equals 0 and then some arbitrary accumulation time, we can see the advance of the ions as they rotate in that circle to this final position. And if we have that angle that the ions moved across, and we know the time, we can solve the cyclotron frequency, again, using this incredibly simple formula. And so I think it's really important and interesting to note that we're able to achieve some of the highest precision measurements in all of nuclear science with such a simple relationship. But in reality, as I think everyone probably already knows, the devil is always in the details for these measurements. But this particular technique is a great advancement in the field. We're actually able to get a precision mass measurement with about 50 detected ions now, which again is important as we go to the drip lines where producing these rare isotopes can be down to ions per day. So this is greatly improving our ability to access these particular species. And in particular, this is really ideal for these low-rate experiments, things like that Aluminum-22 mass measurement I was alluding to before. And so I'll kind of get into the science case around Aluminum-22 now. Thank you. So there's a lot of really initial excitement about a proton halo in Aluminum-22 based on this initial experiment where they observed this beta-delayed proton emission in this related nucleus silicon-22. The details are maybe, again, a little beyond the scope of this talk, but I'd be happy to expand further later. But essentially, this initial experiment ultimately concluded that a halo structure could exist in Aluminum-22. And so that kind of brings us to this question of what should we see if Aluminum-22 was, in fact, a proton halo? And there's kind of three main signatures. One, this valence proton in that nucleus should be very weakly bound. Essentially, only a small amount of energy should be needed to pluck that off. And so we call that the proton separation energy, or SP. And from a quantum mechanical standpoint, that valence proton should exist in this S1 half shell. And that is characterized by this very large spatial diffuseness and low binding energies. And then last but not least, that nucleus should exhibit a very large charge radius. If we have that proton outside the nucleus, then it should be a significantly larger size. And so that led us to do our first ever mass measurement of Aluminum-22 at the Facility for Rare Isotope Beams. And this is the mass spectra we saw here. And we were able to determine a very small proton separation energy existed for Aluminum-22 of about 100 keV. This measurement was also repeated at a Chinese storage ring experiment, and they also were in very good agreement with our result. And so that then brings us to the other two key signatures. And for those, we really rely on both theory and future experiment to actually understand whether a halo exists in Aluminum-22. And so I'll kind of get into a little bit of the details of those now. So one of the first nuclear theory models that we investigated when looking at this case was the shell model. So this is a pretty standard nuclear theory, nothing too special, but it essentially provided us really good agreement with our experiment. They replicated the proton separation energy quite nicely, giving us a lot of good confidence that this model was understanding the physics under or on the inside of this particular Aluminum-22 nucleus. And there was a little bit of confusion in this particular case about the Aluminum-22 ground state. It was thought to most likely be this 4+ state here based on this beta decay observations. But the challenge there is that the likelihood of that valence proton being in the S1 half shell is relatively small. It's only about 29%. And that is not sufficient for a proton halo to exist. And so there was some thought that, well, maybe the ground state isn't 4+. It could be this different 3+ state. If we look at the related nucleus, fluorine-22, it has a very low-lying 3+ state, separated only about 70 keV. And that particular state has a larger probability of that valence proton being in the S1 half of about 38%. And it is quite possible that that could be the Aluminum-22 ground state, again, giving us hope that a proton halo potentially could still exist. And so, unfortunately, or I guess maybe that's not the right term, but at EFRIB, there was a nice experiment that was run recently which had this nice beta-delayed alpha emission observation for the Aluminum-22 nucleus. And they were ultimately able to fix the ground state to this 4+, which, again, is not favoring a proton halo to exist. And so that kind of brings us to the last kind of question. in those 3 points, what if we were able to observe the charge radius? That will definitively tell us whether a halo structure is present. And so there was, again, a nice, very recent result from a laser spectroscopy group at FRIB, where they were able to directly measure the charge radius. And they were ultimately found that there was no enhanced radius for the aluminum-22 nucleus. This plot here is giving you an idea of the absolute charge radius. And if aluminum-22 is a proton halo, we would expect this radius to be much larger, somewhere up here. And so just to give you a little bit of a summary and an outlook, there's a lot of really exciting interest in aluminum-22 based on our initial experiments, both at initial isospin asymmetry, and then our mass measurement, which showed this exceptionally small proton separation energy. We had a lot of theorists weigh in. Ultimately, they thought a proton halo shouldn't exist. There are some other studies that I didn't get into that maybe said a deformed nucleus could have a halo. But ultimately, some latest experimental evidence has fully ruled out the possibility of a proton halo in this nucleus. And so with that, I would like to just thank, of course, the experimentalists and the collaborators who made this result possible, and of course, all the funding agencies for supporting this work. Thank you very much.